the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is an application video for students who've already gone through least squares problems in linear algebra. In fact, this is commonly taught at the very end of linear algebra or near to the end of linear algebra. And it's a very nice topic because it's, well, short. So let's go ahead and dive into it here. Before we get too far, I just want to make a mention here. The notation that I'm going to be using is slightly different, or actually significantly different, than what we've been using this entire course. And that's only because we're trying to match what is used in engineering and physics and whatnot. So instead of AX equals B, we're going to replace the matrix A with the matrix capital X. That is called the design matrix. And then we're going to replace the vector X with the vector beta, and that'll be called the parameter vector. And finally, we will replace the vector B with the vector Y, and that is called the observation vector. All of these names, well, at least the observation vector name, that will become obvious when we get there. The other names are just kind of names that you're going to have to remember. So let's talk about the concept of building what I generally call a line of best fit, but they're most often called least squares lines or lines of regression or regression lines. But anyway, let's talk about how that's done mathematically. You've likely seen a regression line if you've taken a course in statistics, or if you've seen some data analysis in a newspaper or something like that, if anybody ever reads a newspaper anymore. And the idea kind of goes like this. You have some data points that somebody's handed you. Now, this is not clean data. This could be very imperfect data, so it's real world data, but somebody has come along and handed us some observed data points. And this is why we call those Y values the observed values. And when I say the Y values, I really mean the right-hand side vector that used to be called B in our matrix equation. Well, in these applications, we're going to call it the observation vector. And the reason why is these are a series of data points that we have observed, a series of outputs perhaps. And because I want to, the example I'm going to use to build the concept is an example using something that I love. I have played role-playing games since I was a child. Specifically, Dungeons and Dragons. I've played that game since I was around 8 or 9 years old. And to this day, I still run a game for a group of mathematicians and biologists. So I think that will provide a really strong example of building a least squares line. What I want to do is say that somebody hands me a bunch of data points and I want to fit a line of best fit to those data points. Now, the line of best fit need not go through any of the data points. What's important is that the line of best fit is really the best possible line that can be used for approximations when we are not dealing with points at x sub 1 or x sub 2 or x sub 3, but instead values of x in between. So for an example, again, completely made up, but let's pretend, and if you don't know anything about Dungeons and Dragons, that's fine, that's not required for this conversation, but let's pretend that somebody's come in and they've said, listen, when you have a character, for example, a fighter, you have levels, right? So as you're playing this character, they level up just like in video games or something like that. In fact, D&D was kind of the original video game, except it's played live. And maybe you want to do an analysis of how much damage a specific class, which is also sort of like a profession, how much damage a character with that class would do based on their level. And you do an analysis and you find the following information. L will be our input parameter. It'll be what level you observed specific damage outputs at. And D will be, well, those damages. So for example, you might have observed that a third level fighter on average in any given round, which just means in any given turn that that player or character has, on average they might do, let's just pretend, 13 points of damage. And then later on, you have enough data from people who've played the game long enough that let's just say at 7th level, maybe 100 respondents to your query, tell you the damages that their fighters do at 7th level, and so you aggregate that data, you average it out, and let's just pretend for ease of numbering that the average damage per round for a 7th level fighter is 25. And then using the same tactic, you find out that an average 10th level fighter does, let's say, 32 points of damage per round. And finally, let's say that an average 15th level fighter does something like, oh, I don't know, let's just make something up, 43 points of damage every round. Remember, the damages are our observations. It's based on a statistical analysis, an aggregate of a lot of people playing the game over many years. And we could take that data if we wanted to, and we could plot it in Desmos or Excel or something like that, and have Desmos or Excel create a LeastSquares line for us. But let's pretend as though we want to get real crafty and we want to use some of our mathematics. Now, I get the idea that somebody says, well, if I can have a computer do it for me, then why do I need to know how to do it? You, being a student in a linear algebra course, are going to be a developer. And when I say a developer, I mean you're getting a degree. You're not getting a degree to be a consumer of information. You're getting a degree to develop tactics and information and new modeling techniques and whatever it is. You will be the future creators and developers. And because of that, you can't be mentally lazy. You have to know why things work so you can build better widgets. And to be very honest with you, it's an incredibly easy and entertaining process to really find the line of best fit. So let's go ahead and continue forward. So those are our points. And like I said, those y values, which I was using D, but that's okay. Those y values are called the observed values. Now, again, the point here is to create a line that is the closest representation for that data. We don't know what the line is, but we know that every equation of a line is like y equals mx plus b. However, because we're dealing with industries that are not like our math courses, nobody likes mx plus b. Instead, they like y equals beta naught plus beta 1 x. There is actually a great reason for this notation. It just is not apparent initially, but the reality is this talk about building a line of best fit can be grown to build a parabola of best fit or a cubic of best fit, and so on and so forth. And so every time that I need to add another term to this, well, if I started with mx plus b and I want to create a 27th degree polynomial to fit my data, I will run out of letters in the alphabet. So it's much better to use subscript notation for our coefficients. Now, the next line is the only line I think here that will seem kind of weird to you. So before I go ahead and write down the next line, I want to showcase something with my data down here, and I will take my time building my showcase. So those are our 4 data points right there that we're going to use to build a model so that we can make predictions about how much damage on average a fighter will do based upon their level in a D&D game. Now, if you take a look at this data, not all of it fits on the same line. But what we want to do is we want to find a line that will minimize something. We want to minimize the error. And maybe that's the line that does that. Now, I actually don't think that is, so maybe I'll try something like that. That's actually probably closer to the line of best fit. But what does it really mean to have a line of best fit? Really, when I was graphing that line, there were 2 things I was considering. The slope of the line, but also I was just considering how close that line was fitting to those points. And that last little statement, how close is the line fitting to those points, is critical. So let's talk about what that means. Well, if you take a look at that vertical line right there, and we could draw another vertical line to the best fit line, or our line that we think is the line of best fit, all these little vertical lines that I'm drawing in here, they are somewhat important for this discussion. In fact, critically important for this discussion. Each of those is called a residual. Now, some people will call that the first residual, and then this up here would be the second residual, and there would be the third residual, and so on and so forth. In general, we just call them the residuals. That is basically the error that we're seeing in our approximation. The observed y value is the blue dot. Our approximation to that observed y value is this green dot right there that falls on our line of best fit. So you can think of these observed values as little bits of error. And we really want to minimize that error, to build the line that minimizes all of those errors. Now, if you think about this, minimizing all of those errors means I'm going to have to sum them up. And something about that sum is incredibly important for this underlying concept. Again, we're just defining the residual to be the difference between the observed value, x sub I, y sub I, and the respective value on the line that we've just created, which we don't know that line at all right now. It's just y equals beta naught plus beta 1 x. Of course, the y value for the corresponding x sub I here is going to be y equals beta naught plus beta sub 1 x sub I. That's the y value associated with x sub I, but our actual observed y value is y sub I. And as I've been stating, our goal is to find beta sub 0 and beta sub 1 that minimizes the sum of the squares of the residuals. I didn't say that before, but I'm saying that now. We want to minimize not only the sum of those residuals, but the sum of the squares. The resulting line that we get is called the least squares line, or the line of regression of y on x. The resulting coefficients, beta sub 0 and beta sub 1, are called the regression coefficients. So that is the concept, the underlying concept of what we're going to do. However, how in the world do we build that regression line without having a computer in front of us? Well, I gotta be honest with you, it's pretty darned easy. So let's build the solution. Well, let's start with the fact that we were given a bunch of data points. And noting that we have something kind of special. We have an approximation versus an observation. We observed that at x sub 1, the output was y sub 1. Or in the case of our D&D example, we observed that when a character was level 3, the damage on average was 13 points of damage per round. Of course, that's just an observation. That doesn't fit our line at all. So we know that our line evaluated at level 3, for example, is not exactly going to give us a damage output of whatever I said it would have been, which was 13 points. So our line isn't actually fitting that. It's approximately that, but it's not exactly that. If this is 13, well, that value is probably somewhere around, let's see, these are steps of 2.5. So maybe a damage output of 15 or something like that is what the line would predict. So there's some error there, right? And of course, we can do the same thing for our second damage output. We said that at level 7, the output, the y value, should be 25. That is, we were saying y sub 2 should be 25 when the input was 7. Of course, that's not exactly what our line gives, but it's an approximation, and we keep doing this down the line. Now notice what we have there. Doesn't that look sort of like a system of equations? It's not an equation because it's an approximation, but it is a system of approximations. And as I'm alluding to, this can actually be written as the matrix equation x times beta, the vector beta, is equal to the vector y, where x is the matrix where the first column is all ones because that's actually the coefficients of all these beta sub zeros. And the second column is x sub 1 all the way down to x sub n because those are the coefficients of beta sub 1. And beta, the vector, is going to contain beta sub 0, not beta sub 1, and beta sub 1. I don't know why I wrote that as beta 1 and beta 2. It should be beta 0 and beta 1. And finally, the right-hand side vector y should, well, be all the y values, y sub 1 to y sub n. So again, if I want to find out what beta naught and beta 1 are, it's equivalent to solving this equation. However, we know that equation does not have a solution. Now you may say, wait, how do we know that equation doesn't have a solution? Well, it's because all those data points do not lie on the line, unless they are all linearly related, but that's likely not going to be the case with any real-world data. So because there's not a single line that goes through all 4 of these points simultaneously, there's no solution to that matrix equation. What do we do? Well, as I'm saying there, unless all the data points lie on the line y equals beta naught plus beta 1x, there will not be a solution to that matrix equation. However, it turns out that finding the beta that builds our least squares line is going to be equivalent to computing the least squares solution of that matrix equation. In other words, we want to say, well, since there's no way to find the exact line here or the exact vector that will solve this equation, let's get the best possible fit. Let's just find the vector that is the best possible solution without being the exact solution, since there's not an exact solution. Oh, hey, you know what we've gone through recently? Least squares problems, which minimize the distance between this output vector and this left-hand side vector. That's the whole point of the least squares problem, is to minimize the distance between the left and the right-hand sides of that equation that's not solvable. So if you want to do this, you can actually easily do this with this example right here. I mean, I just made it up, so I don't know how the mathematics is going to work, if it's going to be terrible or if it's going to be good, but let's go ahead and try it out, right? So let's build a matrix X. Notice how that matrix X is built. The first column of the matrix is just ones because the equation of the line that we're dealing with, this guy right here, is 1 beta sub 0 plus x, the x value times beta 1. And our x values in our data are 3, 7, 10, and 15. So the first column is going to be the coefficient on beta sub 0 in our linear equation, which is always going to be 1. And the second column is going to be the coefficient of beta sub 1 in our linear equation, which is x, the x value that is, and those are 3, 7, 10, and 15 in this very fictitious case. Again, the vector beta is beta sub 0, beta sub 1. If you imagine multiplying that vector against the matrix X, you would get 1 beta naught plus 3 beta 1. And then the next row would be 1 beta naught plus 7 beta 1, and so on and so forth. And finally, the vector y is just the vector filled with our observed outputs. So let's go ahead and fill up vector y. Now I hope you would agree, the columns of our matrix X here are linearly independent. That's incredibly important because we have a theorem we recently learned that is going to be significantly helpful here, given that those columns are linearly independent. And that was theorem 14 from the textbook that I use. The name of the theorem is the uniqueness of least squares solutions. If the columns of A are linearly independent, then I happen to know that A transpose A is invertible. Not only that, but the least square solution to AX equals B is unique. And that least squares solution has the form X hat equals A transpose A inverse times A transpose B. Now there's a lot to digest here, but we've already proven it in a previous video. The reality is this came from the fact that normally you would have to solve this system of equations. It's called the normal equation for AX equals B. But if A transpose A is invertible, well, then you would get that up there. And I have mentioned in the previous videos that often I really don't like to find the inverse unless the matrix is small. And in this made up case involving D and D, the matrix is actually small. So let's go ahead and find X transpose times X, because that's the equivalent of A transpose times A, then find the inverse of that, and also find X transpose times Y. Again, that's because we're actually dealing with this equation, and since the columns of the matrix X are linearly independent, we know that the least squares solution to this matrix equation is going to be X transpose times X inverse times X transpose times Y. So let's go ahead and figure out what X transpose times X is. Now something I want to mention here and I've mentioned it in a previous video, but when you take X transpose and multiply it against itself, you get a symmetric matrix like this, where this entry is the same as that entry. So that speeds up computation significantly. Also, when you're doing a least squares process like this, notice the first row, first column entry is always going to be the dot product of 1, 1, 1, 1 with itself, or basically the first row with itself. And that first row is just going to be full of ones, at least in these problems. So for example, if you wanted to do a quadratic fit for this data, not that we're going to do that here, but if you wanted to, you could say, well, a standard quadratic would be of the form y equals beta sub 0 plus beta sub 1x plus beta sub 2 x squared. And when you build a matrix representing all of the equations, you'll have a column representing all the 1 times beta sub 0. And that's exactly what our first column was there. So you will always have a first column being full of ones. So it's kind of nice about that. Anyhow, there goes our X transpose times X. Now let's go ahead and find its inverse. Now I'm not going to tell you that this is a nice, clean, pretty inverse because I just made this problem up, which is always a bad idea. But let's go ahead and do it anyway. And as I have a habit of doing, I leave that fraction on the outside of this for now. I also need to find out what X transpose Y is. So let's go ahead and do that. All right, and then we get to that point right there. Now what we're going to do is take our X transpose X inverse and multiply it against our X transpose Y. Let's go ahead and do that right now. So we get this as our answer. Well, what the heck does that mean? Well, it means that this line right here is built of the coefficients from this vector. Remember, B naught, which is 2014 over 307, is the constant in our linear equation. And B sub 1, which is 761 over 307, is the coefficient of X in that equation. Let's see how good this fits our data. So here's our data right here. And over on the left-hand side, you can see I typed in the equation that we had found. It's the least squares equation that we think should work. So let's go ahead and see if it does. Well, that looks really good. It's a pretty darn good fit. Obviously, none of the points actually land on it. It's a very early algebra mistake for people to think, oh, every best fit equation has to go through 2 of the points. Nope, that's not true. That's not true at all. Now, what can you do with this? Well, you can now make predictions off data. That is, I don't need to worry about level 15 characters. Now I can worry about what does the level 20 character do. I can make a prediction based upon that by looking at Y evaluated at level 20. So I'm just going to type that in here, except I think I needed to call it F. So F of X is what we'll call the function, and F evaluated at 20 tells me immediately that roughly 56 points of damage per round is what a 20th level fighter would deal. Of course, this is not very realistic in the game mechanics sense, because if you want a really good game system, the curve should be logistic and not linear. Another thing that I want to mention here before I escape from this video is that you can double check that your work is correct by having Desmos show you the linear regression line. The way you do that is you type in y sub 1, because it's the output variable that Desmos has seen, is approximately, that's the tilde, mx sub 1, x sub 1 because that's your input variable, plus b. Notice that Desmos gives you a lot of other information. M is 2.4883, B is 6.56026. If you take a look at these coefficients here, 2014 over 307 is that 6.56026 blah blah blah. So we were really good with that. And 761 over 307 is 2.478827 blah blah blah. So we did exactly what Desmos worked to do as well. By the way, also, notice it says residuals. I've never seen that, so I'm going to click plot. And that's pretty cool. It's actually giving us the distances between our data point and the line. That's what that black dot is, the distance between This green dot in our blue line is that data point right there. So you can see they actually plot out the residual, so you can see when you add up the sum of those squares. It's actually minimized when you do that. One final thing I want to say, that black line is the line that we graphed. That blue line is the regression curve that Desmos graphed. Notice they are the same line because we are awesome. All right, that's all I really had for this video. I hope it was interesting and it helps you out in your quest to defeat linear algebra. Roll initiative and do some damage.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine, just